what if I want to not do this kind of analysis problem, but I want to add something to an existing circuit so that the current in some branch is say 5 milliamperes, right? Synthesis problem rather than analysis problem. And immediately I found there is nothing. So this is the approach I took, and it becomes a nice game of solving puzzles and kind of a detective game, and in that way even teaching of circuit theory becomes very interesting. So let me, so there's going to be some mathematical preliminaries, and what I'm going to show is that if you deal with unknown systems, which is the reality in most engineering problems, you can take an approach of taking a few measurements and from that to extract the design information that you need. Right? You don't have to completely model a system. You just need enough information to design whatever you are going to design. It's like a doctor, you know, he doesn't, when you go to him, he doesn't immediately tell you to X-ray and CT scan and all this. He takes a few measurements, from that he prescribes the medicine. So with this approach, we don't want to deal with systems which are completely modeled. We would like to deal with unknown systems to which we are going to apply a voltage source or a resistance or a capacitor or something like that. Can we design these elements by taking a few strategic measurements? So this is the sequence that's going to happen. Mathematical model is required in most engineering design, but the reality is most engineering designs don't have mathematical models. Most engineering systems are not linear, but if you operate close to an operating point, it can be approximated by linear equations. In practice, systems are very complex. And one example that I like to give is there is a hydraulic network supplying water to a city. And you want to add another pipeline. How are you going to add the size so that a certain amount of flow occurs? You don't know what is existing. You can solve this kind of a problem with a few strategic measurements. All right. So this is the kind of problem I'm going to talk about. There is an unknown linear system to which I'm going to add a new element, and the design objective is to prescribe a current flow in a certain branch. Can I solve this problem? Answer is yes, with 3 measurements. Why 3? You will see in a minute. Okay. This kind of a problem, where we have a complex network, and we are going to only try to adjust, say L1 and C2, 2 design elements, and the objective is to assign 2 currents. Can we solve a problem like this in circuit theory? Answer is yes, and I can tell you what measurements to take and how many, and what equations to solve. So these are the objectives: to solve a design problem without knowing the system. So here's a simple motivational example. I have an unknown circuit. Unknown circuit. I have a source which is my control variable, and I'd like to assign the current in some branch, right? I want that current to be, say, 10 milliamperes. How can I find the source voltage that I need in order to assign them. So the challenge here is, I don't know this circuit. Even if I knew the circuit, the way we normally teach circuit theory, you cannot solve this problem. I am claiming that I can solve this problem with a few measurements. So what are the measurements? I will set the voltage, measure the output. Set the voltage, measure the output. I can do 2 such measurements. From that I can answer what voltage is needed for a given current. Okay? Are you guys with me, the EE students? Can you solve this problem? You don't know how to solve this problem, right? Because all the circuit theory is all analysis, it's not synthesis. So my point is, let's try to teach circuit theory in a more challenging way, in a more constructive way. So here's, I want to make this current equal to some value Y star. What is the required input U star? So I say take a few measurements, take 2 measurements, set U equal to U1, measure Y1. Set U equal to U2, measure Y2. From these 2 measurements, you can solve the problem I posed. How is that? It's a linear system. Being a linear system, the output is a linear function of all the inputs. Okay? Now, the source you are manipulating, U, may not represent all the sources. There may be other sources inside that unknown circuit. So those will induce some initial current, which is the 0 input current with respect to this source. So there is going to be a Y0, and then it will be a linear function of this source. So the equation is going to be of this type: Y equals alpha 0 plus alpha 1. If I know alpha 0 and alpha 1, then I know the functional dependence of Y on U, and then I can predict what U is required for a prescribed Y, right? I can invert the equations. In order to know alpha 0 and alpha 1, I need to do 2 experiments, because it's a 2-parameter problem. I set U, measure Y, set U, measure Y. From that data, I can uniquely solve for alpha 0 and alpha 1, and indeed, here's the solution. I don't know what happened. So these are the measurements, the 2 measurements. Y1 and Y2 are the responses to U1 and U2. From those, solve for alpha 0 and alpha 1, and then invert the relationship, and you can find the U star needed for a prescribed Y star. Right? You can try this in your lab. Check an unknown circuit, manipulate a source, and then you can verify whether the predicted value gives you Y star. You can say, well, that's a very simple problem. What about if you have 2 sources and 2 currents that you want to adjust? So here is a problem like that. U1 and U2 are 2 sources. I want to adjust the 2 currents, Y1 and Y2. All right. In this case, this is a two inputs. I will need three experiments, because it's going to be a 3-parameter problem, and you will see why. Because the input-output relationship is like this: initial value G times U. All right, and then the unknowns are 1, 2, 3, 4, 5, 6 unknowns. Each time you set an input, you will get 2 equations. So 3 inputs will give you 6 equations. From those you can solve for Y1, Y10, Y20, G11, G22, etc., etc. And so, is this okay? Hmm? Without knowing the system, by taking a couple of strategic measurements, you can know what input should be applied to get a prescribed output. Yeah, I'm sure.
Fascinated by this. Actually, I'm sorry, but
And it's an unknown system, which is a reality in most fields. So here are the measurements. I took 3 measurements. Each time I set the inputs, measure the outputs. From this data, I can solve for the Y10, Y20, and the G11, G22, etc. You guys should ask questions if you have any doubts right now, because later on you'll forget your own doubt. Is that okay? You set up the problem, how many parameters are needed? You need to do that many experiments to extract only those parameters, not to know the whole system. Let's write a paper together on economics. See, this is why you come to conferences and talk to people from other fields.
Do you think everything is set?
That's really great. I'm so happy. So you see, you solve the problem with those 2 methods and you got now we want Y star to solve for U star. And you can solve. Alright. Now we go to another kind of a problem. This is where we have a source and we have an output. Another type of problem is we want to set a parameter, like a resistor. I have an existing circuit. You can imagine an extremely complicated VLSI circuit or something to which we are going to add one resistor. I want to add a resistor to control the current in one branch. See, my approach to research is to solve the simplest problem. And once I understand that thoroughly, I can extend it to a very complicated scenario. And you will get amazing results like that. So here is the situation. For this I need to know, I'm going to use what is called Kramer's rule from linear algebra. Ax equals solution of Ax equals B. So Kramer's rule says that if you have a high order linear equation and you don't want to solve for the complete vector, but you want to solve for say x5, you may have x1 to x100, but you are only interested in x5. What is x5? x5 is determinant of a5 over determinant of a. Alright? So the solution of various variables in a linear equation is going to be a ratio of determinants. And these determinants will be functions of parameters. So it's good to know what kind of functional dependence is this. So here is a little, again, starting from very simple things. Let's say we have a matrix depending on one parameter P, and the coefficient matrix of that parameter is A1. Right? Let's suppose rank of A1 is R. Then it will turn out that the determinant of A of P is a polynomial of degree at most R in P. Alright? If alpha R is different from 0, it will be a degree R polynomial. If it is 0, it will be less than R. So, turns out, if you have several parameters, it's going to be a multivariate polynomial. P1 up to PL, and each P1, Pi will occur with degree Ri. So you get all right, I have only 5 minutes. That's fine. It's a bit challenging, but I'll try. So you have a polynomial like that, okay? You're going to get, so in general, now you're going to have to run. You get a ratio of polynomials, ratio of determinants, which are going to be parameterized by polynomials. All right, so if you can bear with me, we are going to, so if you solve a parameterized set of linear equations, you will get a ratio of polynomials, right? So that tells you how many measurements you need. So here is a typical application. Unknown circuit to which I am going to add one resistor, and the objective is to control that current. All right. So to make a long story short, that current, the dependence of that current on that resistor is going to be polynomial of degree 1 divided by polynomial of degree 1. So alpha 0 plus alpha 1 R divided by beta 0 plus beta 1 R. And then you can normalize, because both betas cannot be 0. So divide by one of them and you end up with equation 9. 3 parameters. 3 experiments are needed to extract those 3 parameters. Once I do those 3 experiments, what are the experiments? Set the resistance, measure the current. Set the resistance, measure the current. From those, solve for alpha 0, alpha 1, beta 0. Once you know that, there are some special cases when the determinant is 0 and so on. But in the most general case is a 3-parameter problem. And so, okay, it turns out that Thevenin's problem, since we are running out of time, we are going to have to do some homework. Thevenin's problem is a special case of this. It's a 2-parameter problem. And what do we do in Thevenin's theorem? We measure the open circuit voltage and the short circuit current. Well, you don't have to measure those. You can find out from any 2 measurements what those are. So in Thevenin's problem, you're going to have this kind of a situation. You need to estimate, predict 2 parameters. 2 experiments will do that. And then you will get the functional dependence. So here's here's the graph of current versus resistance. So if you want a certain current, you can predict what the resistance will be. If you want to bound the current between 2 limits, you can find out the range of resistance. Also, you know the maximum current that you can get from that circuit and the minimum current. And you can find the power also. So all this comes out of doing 3 measurements. Thevenin's theorem is a special case where the rank of the matrix drops from 3 to 2, and then you have only a 2-parameter problem. So the interesting point here is that you don't have to short circuit anything, and you don't even have to open circuit anything. You can take 2 arbitrary measurements. From those, you can find the short circuit values and open circuit values. But many times you cannot short circuit 2 terminals, in a circuit. All right. So now we start running. You can do the same problem with 2 resistors and a current. Um, in that case, you need 7 measurements because it's going to be a 7 parameter problem. You can do the same procedure. Once you found that, you know what currents to adjust. All right, special cases. If you have M resistances, etc., etc., nobody said we are unable to complicate things, right? So you can calculate power, how much power can be extracted from that circuit by adjusting resistances, etc. So you can this is an interesting problem where I want to adjust a couple of resistances to control the power in 3 different branches, and I can find the corresponding functional relationship and extract what values satisfy each of the constraints, and then intersect. These are the values that satisfy all the constraints. You can do the same thing with an AC circuit, except now you have complex numbers. All right. So once again, in that circuit, here's a typical problem you can solve. You can put magnitude and angle constraints on the currents, and then you can solve for L1 and L2 that achieve that. Typical solution with a final result is the intersection of the values attaining each of the constraints. Let me go to so basically once you are in AX equals B, you have access to mechanical systems, hydraulic systems, chemical, thermal. So I solved mechanical problems like this, where you can adjust the spring values and mass values to get certain displacement. So I'm just going to run through that. Even in civil engineering, there are truss structures, and you want to limit the displacement of the truss points by adjusting the thickness of the truss elements. It's also a linear problem. So there is an example like that. I like this hydraulic system example. You want to, like I said, you have a hydraulic network, you want to add a branch or 2 branches. You want to limit the flow in those to a certain amount. You want to know what size should be put. Well, you can do a pilot experiment, put some pilot lines and measure the flow. If you do it 3 times, you can predict the functional relationship. So a system like that where you are trying to add a line, you want to know what should be the resistance. You can find out from the same kind of theory, the set achieving certain flow limits, etc., etc. So I think I can conclude here by telling you that by making Thevenin's theorem a property of linear algebraic equations, I got access to all these results. And now it remains for people in mechanical engineering and hydraulic engineering to interpret these according to their own fields. Okay, so thank you once again for this opportunity, and I wish all of you the best in your careers.
Okay, thank you, Speaker Dr. Yeah. This is highly technical and very mathematical. So, if he can kindly hand forward the materials to you, probably you can go through and then learn a lot of things. And this is very good thing that, like when you are applying the Thevenin's theorem, so you have to open the circuit, or you have to have a short circuit current. But here, any practical network, you cannot do that. So you can have your mathematical things and do all these things. Thank you very much. So before inviting questions, we shall take two questions. Before inviting Dr. Shahriar, one who wants to hand over his book written by him to our speaker. So please.
Thank you very much. I don't want to miss this opportunity because I think today it is a major occasion. I am actually attending Sir's lecture after 25 years. Right. So I have attended his class, EE605 control systems, based on which I had an exam and everything. And it's been 25 years. 25 years later, I'm attending his class again. I think that's a major thing. And so he's, of course, one of the foremost authorities of control systems. So it is very humbling that I also kind of wrote down whatever I had in my mind, and I was also thinking what he would think of it. So I'll find out. I'll just give whatever I wrote. It's a book called Control Systems, which is for mainly our undergraduates, which is of course a very low level, not anywhere close to what he has, but it's a very humble effort. I want to take this opportunity to hand it over to him.
I'm inviting questions.